Hello, everyone. Today we're going to talk about scatterplots, correlations, and regression. All right, let's start with some definitions. A correlation exists between two variables when the values of one variable are somehow associated with the values of the other variable. A linear correlation exists between two variables when there is a correlation that can be approximated by a straight line. So correlation, we take two variables, somehow they're going to be associated. If they're associated when we plot them on a graph in a straight line, we would say that's a linear correlation. A scatter plot is a plot of points. We write points as x comma y of quantitative data with a horizontal value of x and a value represented by y on the vertical axis. So we have our two different variables, x representing one variable, y representing the other variable. We plot them as points. Plot every single piece of data. That gives us what's called a scatter plot. So big caution here. So there may be a correlation between beer consumption and weight, but that doesn't conclude from the statistical evidence that drinking beer has a direct effect on weight. Meaning, I could, let's say, be a heavier weight and not consume any beer, or vice versa. I could be a very small weight and consume a lot of beer. Just because there's a correlation does not imply that is the causation. So big key here, correlation does not imply causation or causality. All right, let's look at some examples. Right. So listed below are the overhead widths of seals measured from aerial photos and the weights of the seals. The purpose of this study was to determine if the weights of seals could be determined by overhead photos. Okay. So in our first scatter plot, we can see there tends to be a correlation. If the width of the seal in centimeters is greater in our photo, then the weight is heavier. So the bigger the whale, the heavier the whale. We can see there's a correlation there. Doesn't it mean there's any causation? We can see there's a correlation. So the second one is kind of a silly example. Each point represents the heights of presidents, and the other one represents the heights of their opponents. Clearly here, we can see there is no correlation at all. The height of the president, the people running for president, doesn't make one a candidate, better candidate over the other. So we can see there's just random dots and all over, they don't form any sort of shape. So a few more definitions. We have what's called the linear correlation coefficient, which we denote by R, and it measures the strength of the linear association between variables. So this value is always between -1 and 1. So if R is close to -1 or 1, it means there appears to be a correlation. If R is close to 0, then there's no correlation at all. So if we want to find R for our last examples, which oftentimes to find R, we'll use a statistical data technology method. Rarely are we going to compute R ourselves, but we can use one of our pieces of technology to find R. But just as an idea for now, 0.948 would be R of my first picture. So we can see there clearly is a correlation. The bigger the seal in width, the heavier the seal is. Makes complete sense. There's a correlation. And then in our second picture, we have -0.144, which is very close to 0, far away from 1 or -1. And we can see there's no correlation at all. So the closer the number is to 1, the more of the correlation. Farther away from 1 and closer to 0, there's no correlation at all. So we'd say a strong correlation for the first one, no correlation at all for the second one. Right. So we have what's called regression lines. So again, we're going to use technology to find this. We're not going to compute it. I'm going to explain it here, but for this class, we're going to use technology to find everything. And we'll do that all in our labs, but I'm going to introduce it now. So given a collection of paired sample data, the regression line, or sometimes called line of best fit or least squares line, all interchangeable, all mean the same thing, is the straight line that best fits the scatter plot data. We're going to write this as y hat, so this little caret on top of the y is called y hat, is equal to b naught plus b1 of x. So this point b0 or b sub 0, b naught, all interchangeable, means the same thing. So b sub 0 is the y-intercept of the line, and b sub 1 is the slope of the line. The equation algebraically describes the regression line. So if you can see in our corner here, if we were to use one of our pieces of technology, we can be given the regression line here. We're given a y-intercept, we're given a slope, and we can plug that in and find that line of best fit. So we'll talk more about that later once we get to labs, but for the lecture portion, this is how we find it. We're going to use our technology to find our y-intercept, we find the slope, and that gives us this red line here. So we can see that the line best fits this data. Another way to think of it. So if we were to push all those points together and create the best line that fits the data, it would be this line in this case. That's going to be it for today's lesson. I hope everyone has a great day.